Okay, welcome back. So I left you with the little problem of calculating the mass of the Sun using Kepler's third law, just putting in the orbital parameters for the Earth, obviously. So we have A as 1 AU, so 1.5 10 to 11 meters, and P is 1 year. So I'm sure you've calculated this a few times yourselves now, so just over 3 10 to 7 seconds in a year. And if you put all those numbers in, you do indeed get 2 10 to the 30 kilograms, the mass of the Sun, one solar mass. It's the very first thing we had in this module, and here you can see now where it comes from. Now, of course, on the left-hand side there was it's really the sum of the mass of the Sun and the Earth, but M2, the mass of the Earth, is 5 orders of magnitude smaller than M1. So in terms of that sum, it's really negligible. So basically all you're doing here is calculating the mass of the Sun. Okay, so that's Kepler's third law in action. So let's just revisit a few more things here. So this is what Kepler himself found empirically, observationally, so that to be p squared is proportional to a cubed. There's a little exercise at the end of this lecture where you can prove that from the data yourself. If sometimes you might want to use Kepler's third law in this form and with these units. Again, it's not core to this module, but sometimes it's useful as a sanity check. So obviously, if you have the period in years, masses in solar masses, and A in AU, then this it actually works as an equation then. But normally, you'd be using the form of the constants, 4 pi squared over g in it. Okay, so a few things now on real orbits before we get to how we actually use all of this to address real systems in the next lecture. So we assumed circular orbits where we derived Kepler's third law there. But normally orbits are actually elliptical, not circular. And so ellipses are described by these two variables, the semi-major axis A and the semi-minor axis B. So these are the equivalent of a radius for a circle. If we have a look at the diagram here, so here's an ellipse, okay, and here's the semi-major axis A, which is obviously half of the long axis here, and semi-minor axis is this distance here from the center to the nearest point on the ellipse. Okay, so that's A and B. And just a couple of other things on here. So again, this is Kepler's first law was that basically one of the objects is at the focal point of the ellipse. A focus has 2 focal points, and you can put one of the stars at one of the foci, and then the other star will go around the ellipse like that. Okay. And so just introduce a little bit of terminology to explain how to describe how elliptical an orbit is. So here we introduce the term called eccentricity, E, which is just given by this relationship here. So this is the square root of A squared minus B squared, normalized by A again. Okay. So you can see that for a circle where A equals B, okay, then the eccentricity is 0. So for orbits that are nearly circular, then E is 0. So something like the orbit of the Earth around the Sun, the eccentricity is 0.01, something like that. So very close to being circular. So here we've got a little illustration of how eccentricity works for different, as orbits get more and more elliptical. Okay, so here's the circle at E of 0, and then you can go all the way out to very extremely eccentric orbits like E equals 0.9 here. This would be something that is typical of a comet orbiting the Sun. So they spend a long time in the outer solar system out here, moving very slowly, and then they come in and they whip around the Sun very quickly, and then go back out again. Okay. And so that's the second of Kepler's laws, the idea of a line joining the sun to the orbiting body, sweeps out equal areas in equal times. That basically tells you that it moves slowly out here and it moves very quickly in here. So, handily for us, Newton's form of Kepler's third law also applies to elliptical orbits, even though we derived it for the circular orbits. And all you need to bear in mind is that the A in that equation now is the sum of the semi-major axes of each of the individual orbits, rather than the sort of circular radius R1 and R2 as we had before. So here, the A1 and A2, where these are the semi-major axes of each of the elliptical orbits of the two stars. And that's just as well. You know, if you're really interested, I wouldn't recommend it. You can look entirely at the derivation of Newton's law for elliptical orbits, but it occupies about 5 pages of algebra, whereas obviously we just did it in 3 easy steps, assuming circular orbits. Again, just to illustrate, here's a little animation. Okay. If you go to this web link, then you'll see an animation of how stars on elliptical orbits orbit around the common center of mass, showing you again that they move slowly out here and more rapidly in here. Okay, so the last thing here is just to introduce a bit of terminology that we're going to use in the next lecture, because the inclination of the orbital plane of binary systems out there in the universe can be orientated in any random direction, of course. And so we need to introduce this bit of notation that is the inclination of the orbits to our line of sight. So here are the two stars orbiting around each other, and that line there represents the orbital plane. This is our viewing point over here, and so this is the inclination angle I here. Okay. So you can see that if I was 0, then the stars would be sort of orbiting around like this as you see them. Okay, so you'd see the full sort of orbit. Whereas if I is 90, the system will be edge on, and the stars would just be appearing to go to and fro in the sky like that instead. Okay. So just to summarize this lecture, then binaries are the only direct way we have of measuring stellar masses, because we're directly probing their gravitational influence through Newton's law of gravity. And Newton's form of Kepler's third law is the starting point for measuring stellar masses. So in the next lecture, we will start from there and see how we can actually, in practice, use it to measure stellar masses. So I just want to leave you with a little pencil and paper exercise, really. You can probably tell I'm quite keen on, getting to grips with data. So here is the kind of information that Kepler gathered. So you can plot the orbit of the main planets in our solar system, plot their orbital period against their semi-major axes, and this is on a log-log plot, okay? And you can see that it's a straight line. So if you sort of get your rulers out and measure the slope of this line in this log-log plot, you should be able to recover Kepler's third law for yourself. So have a go at that. Just a hint, you might find it more useful to relabel these axes actually with the actual log of the numbers. Okay, and then you probably get the idea a little bit easier about where the gradient comes from or how to measure it. Okay, so I'll leave you with that little exercise. Next time we will look at using all of this for real systems. Okay, I'll leave it there.